And yeah, we're live now. So once again, if you do not like being recorded, please leave. But otherwise, I will begin. And also, check-in code is on the slide right here. And if you want to refer to it later, it is also in shared notes. So there you go. Now then, let's just get right into it. So I want to provide some context. So I tried doing a functional programming workshop last spring quarter, and it was honestly a bit of a mess because I tried to cover a lot of different topics in one presentation. And this is basically what I want to cover with this series, but I've just broken my last presentation up into all different kinds of into 3 different bite-sized manageable pieces. So that's why we're here. Okay, so the link I have up here right now is an interactive editor that you can use in your browser to edit Haskell. It will look something like this when you open it up. And then you can just mess around in here. I actually find the examples kind of helpful to get started with. So these all do things that I will explain later. But for now, you can just add hello world, and it will print hello world. It should print hello world. Oh, there we go. OK, well, if you would like to follow along with the slides, type in your code up above the main, and you should be good to go. So moving on. So what the hell? Why the hell are we even learning Haskell? So like I said before, Haskell is what we call a functional programming language. What the hell does that mean? I'll explain later. But yeah, Haskell is pretty experimental as languages go. But thinking about things in a functional way is kind of interesting, and that's why I'm teaching it. So yeah. So what's good about Haskell? It's got a decent type system, unlike other languages like JavaScript that just go willy-nilly. Haskell is also pretty fast and it's functional, so I'll explain what that means. Cons: it's kind of hard. No one really uses it, so it's hard to maintain Haskell code, and it's not really used much in industry. But that's not why. Again, that's not why we're here. We're here to just kind of have fun with it and do all the things possible with functional programming. So yeah, let's have fun with it. Moving on. So what the hell even is functional programming? So I'm going to assume that most of you have at least some experience with coding in other languages like Java, C, C++. Those are all what we call imperative languages, which basically what you do with those is that you describe a sequence of steps to get to the output. So you're familiar with C++, C++, Java, Python, those sort of things where you have for loops, while loops, variables, global variables, that sort of thing. Okay, functional programming, on the other hand, is a specific subtype of declarative programming, which is basically where you describe what the output of a program is without describing how to get there. So what the hell does that mean? That'll become clear later. But yeah, it's basically set up so that you don't have to worry about the intermediate steps you have to take. So I can give you an example of declarative programming that isn't a functional programming language. So for instance, SQL queries, right? Database queries. So for those of you who don't know, database queries are where you basically pick a table, you have a database, you pick out a table, you pick out a row. So let's say you want to like select a row that contains this query string. You just kind of say it, right? You do like, you just kind of say it. So you do select row where name is Kyle or whatever, right? And the SQL thing just kind of does its thing without you having to tell it how to do that thing. Well, functional programming is kind of similar, but instead you're using functions. But well, you basically have an input, you take the input, you apply a bunch of functions to it, and you get an output. And you don't have to worry about how those functions accomplish the things that they do, but you just kind of do it. That does not mean that we don't. That does not mean, however, that we don't have to know how we don't have to not know how the functions work. We do. We can still write functions that do things that we want to do, and then we can still write functions that do things, and then we can use those functions at other places. But we don't have to worry about how the nitty-gritty, how it works with all the details in memory and whatnot. So yeah, moving on. Oh, the link in share notes doesn't work. Okay, I think you got it. David, checking code is in the share notes. So yeah. All right, I'll move on now. So to elaborate more on the differences between imperative programming and declarative programming, here we have some JavaScript code. Just to get us started. So the example I'm using here is that we have an array called nums that has the numbers 1, 2, 3, 4, 5, and then we're just going to add 1 to every single number. So let's take a look at the example on the left first. So what's happening here is that we have a function called add 1 to elements. And here we have a for loop, pretty familiar thing. And what we do with the for loop is that we have an index that we iterate with, that changes from 0, 1, 2, 3, 4. And then for each index, we just add 1 to the address of the number. That's all well and good for those of you who have had some programming experience, right? Well, here's the other approach, the functional approach that we have on the right. So we have an array called nums as per usual, and then here we define here nums add 1 is the output of the thing we want to do to it. So we want to add 1 to each of those. And what we do here is that we take the thing, we take the array, we call a function on the thing that takes this, that does this. And this basically means that for every single item we have in nums, we just apply this function to it, and then we add 1. So this should give you a general idea of how functional programming kind of works. We take the thing, we apply a function to it. This does that applies other functions to the things inside the array, and then we get a result. That's the basic idea. So now we're just going to get straight into the features of Haskell. So let's start from the basics. These are variables. Haskell is indeed a statically typed language, so there are specific types that you have to assign to variables. For instance, we have int here, we have a string here, char, double, and all the other types you can think of are in here too. Bool, float. Well, those are the only primitives I can think of for now. But yeah, those exist too. And this line right here, well, these lines I have before all the variables are basically how you define types in Haskell. And those will basically get extended to, well, you'll see why they're kind of important to have later on in the next slide, actually. These are functions. So this is how you define functions in Haskell. So this arrow syntax might look a little bit weird to people who have never seen it before. But what this basically means is that everything to the right, to the left of the rightmost type are all input types. So here we have int, and what this means is that this function takes an integer and returns an integer. And of course, sum AB returns A plus B. And notice as well, like the way we're like writing it out is kind of similar to how we define math functions rather than programming functions or procedures. So normally how we would do this in say Java, for instance, is that we'd have a function and then we'd return A plus B, right? Here we don't do that. We just do sum A plus B is equal to A plus B. Pretty simple. Likewise here, we have square. We have a function that takes an integer and converts it to an integer. And we have square a equals to a times a. Lastly, here we have a function square of sum, which returns the square of the sum of the integers. So num is just num. I have a type num here. That's just a generic number type that can mean anything from like integer, float, double, whatever. It's arbitrarily precise and can be arbitrarily large. So that doesn't really matter. It takes two nums and returns a num. Takes two nums and returns a num. And what we do here is that we take sum, we apply it to a and b. That calculates the sum, a plus b. That's what we defined up here. And then we run the square function, and then this returns the square function. Okay, I see we have some questions in the chat right now, so I'll just go through those. How do you interpret the number of arrows? How do you interpret the number of arrows? Yeah. So everything, let me clarify. So everything to the left of the rightmost thing is going to be inputs, right? So sum AB, A is an int, B is also an int, and it returns an int. Yeah. How does the program know what type you're referring to by num if it can mean anything? Well, num is its own separate type that kind of encompasses all number types. So if you give it like a double or an integer, it'll just convert it to sort of a generic number type that is arbitrarily precise. So yeah. Any other questions before I move on? Yeah. Yeah. Yeah, it kind of is like an abstracted superclass. All right. Doesn't look like we have another question, so I'm going to move on. All right. So brief note here on functions in Haskell. Functions don't mean the same thing as what they mean in languages like Java, C++. In Java, C++, and other imperative languages, functions are another way to describe functions are what we call procedures. So you just you put a bunch of instructions in the procedure, and the computer carries them out. Pure functions, on the other hand, are slightly different. So pure functions in Haskell are more aligned to math functions. So they have to give an out. They have to satisfy properties like giving an output. They have to give the same output for any given input, and they can't have any internal state or side effects. So thing goes in, thing comes out, nothing else happens. That means you can't normally. That means that you can't debug functions in Haskell like you normally would in other languages because you can't print anything. Yeah, that is kind of annoying, but it is what it is, unfortunately. But yeah. Does that mean that Haskell can't perform any side effects? No. But there's a kind of complicated workaround that I'll get to in part 3. So yeah. What are the uses of Haskell? Haskell, like I said, Haskell can change. There are ways to like contain state in Haskell. It's just more complicated than how you would normally do it. But it's kind of hard to. It's a difficult beginner topic, so I'll leave that to a future part to explain. So yeah, we're not going to worry about that today, is what I'm saying. So let's talk about conditionals, if statements. Now, the first part is going to be pretty familiar to most people. It's the if-else. So here's a function, is even, that returns if a number is even. It takes an int and a bool and returns a boolean, true or false. So is even n equals if n mod 2. So it's checking if it's even. So n mod 2 is n mod 2 is going to be 0, 1, and just like C or just like C and other languages like that, 1 does kind of mean true in this case. So if n mod 2, then false, else true. Here's another way to do it. So these are called guards. And this basically, what you basically can do is that you can, it's another way to sort of describe conditions. And it's kind of like the function I have, the function I have on the right here, which you would use to describe with traditional math. So let's go through this. So is even n. So if mod n2 equals 0, so if, oh, I should clarify something. So the backticks here for mod make it so that you can apply that mod is a function, and you can apply mod to two different numbers in different ways. So if you just have mod by itself, you have you have to put the two numbers afterward. If you add a backtick, you can use it as, you can put it in the middle of your two operands. So this notation is called prefix, and this notation is called postfix. So I didn't want to worry about that too much today, but yeah. But anyway, so mod n2, if mod n2 equals 0, so if n mod 2 equals 0, the number's even, so we return true, and otherwise we return false. Hopefully that's clear. Guards are the equivalent of statements? Well, yeah. They serve the same function, is what I'm trying to get at. Okay. Now on to the last thing. So Haskell also has what's called pattern matching. So pattern matching is basically what happens with pattern matching is that Haskell identifies sort of a pattern that your function. So say your function takes an argument. If your argument matches a pattern, then it does something. And if your argument doesn't match that pattern, it tries to look for other patterns. So let's take a look at this function, for instance, UCSD species by college. So let's say you're in 6th. That means you're a raccoon. So what this function does is that if the input argument, which is supposed to represent your college, is not 6th, you do not enter this. This is not the correct definition, so we skip over this. So UCSD species by college underscore. Underscore is a wild card, so anything can match this pattern. And if you are not 6th, then you are human. If you are 6th, you're a raccoon. Yes. So that's basically what that does. Any questions before I move on? All right, looks like we're good. We also have where and let. So function. So what where and let you do is that they basically let you define expressions inside a function. So let's take a look at some examples. So let's say we want to write a function that checks if a triangle has a big enough area. And the triangle will take, oh, I forgot to add base and height as an argument here. It's kind of bad, but base and height are supposed to be arguments there, is what I'm trying to say. But anyway, so let's say we want to write a function that checks if the triangle is big enough, and it takes the base and height as an argument. So we can make it so that instead of calculating the area in here, base times height divided by 2, we can just put in area. We can just put in an expression called area and define that expression later as base times height divided by 2. Let basically does the same thing, but the syntax is slightly different. So I've defined a different function called cylinder surface area, and that calculates the surface area of cylinder. So here we have an expression for the area of the circle on both ends. Here we have the area of the side of the cylinder, and then just multiply the two sides and then add the side. So yeah, it is kind of wonky if you haven't seen it before. I agree. But, yeah. So it assigns the first number to base and second to height. Well, I forgot to add base and height as arguments here, but yeah, you've gotten the general idea. Yeah, it is pure math in a programming language. That's the whole idea. All right, moving on. All right. Looks like I have an exercise for you guys. So hopefully you have that editor open from earlier. If not, just go through the slides and click the link. But don't worry, this should be pretty simple. So let's try to write a function that determines if a Pokemon is one of the Gen 1 starters. So that's the 3 Pokemon I have here. That's Squirtle, Bulbasaur, and Charmander. So to clarify, I want the input to be a string, and I want your function to output a Boolean based on whether that Pokemon is one of the 3 starters. Yeah, one of the 3 Gen 1 starter Pokemon. So, and I'll give you the function definition as a helpful hint as well. So, yeah, and feel free to use any of the functions that I listed before, or any of the features of Haskell that I listed before. But I'll give you like 5 minutes to work on this, and then we'll go through it. So, yeah, there you go. There's a function declaration. So, yeah, I'll let you guys do that. And I'll be looking at the chat and you have any questions. And yeah, I should pause the recording. All right, we're back. And let's go over the answer to this problem. So there are 2 ways to do this, actually, that I can immediately think of anyway. So the first method that I actually used was guards. So let me go through that real quick. So is Pokemon starter takes a string. And if the string is Squirtle, or the string is Bulbasaur, or the string is Charmander, you get true. And if not, you get false. You could also do pattern matching. So you just define separate functions for Squirtle, Bulbasaur, and Charmander. Then if there's anything else, return false. Any questions? Multiple users are typing. Woo-woo. It's not working on the REPL.it editor. Oh dear. Could I try it out? Yeah, sure. So let's do. I can't just copy code over. Oh, that's slow. Okay. Create a constructor not in scope Charmander string. That's my error. Oh dear. Let me just do this real quick. Oh my god. Please don't do this to me now. Tab. Okay, does this work? Oh, here. Do I have to? Oh, I forgot to close it. Go. Okay, that seems to be fine. I return false. That's true. So it seems to work fine. Is main equals do necessary here? No, no, not at all. So yeah, the main function isn't really relevant to what we're doing, but yeah. Okay. Well, main equals do necessary. I don't know. Well, we'll go over IO in part 3, so not today. What characters make the arrow? Oh, what characters make the arrow? So it's a hyphen and a greater than symbol. Yes. Oh dear. Okay, that's very nice. Oh yeah, if you have to, yeah, you have to, yeah, when you're entering strings as arguments, you have to do the double quote. So yeah. Are the function signatures like prototypes that can be anywhere in the file? That is a good question. I have not tried that. I, it's good practice to have it right after, but I actually kind of want to test it. So, does this work? It does, surprisingly. It can be anywhere, but don't, because it looks ugly. Oh no. Scaffolding language, I swear. Bad. Yeah, paste your error in chat, Joseph. I'm gonna spend like 2 more minutes on this and I'm gonna move on. So in the interest of time. Parse input error on input equals. Perhaps you need to let it be blocked. Oh, in the world? Yeah, Nishant probably has a problem with his quotes. What the hell? Um, Okay, it's 4:40, so I'm gonna move on from this, but Mateo will still be in chat if you need help with that. But yeah, I'm just gonna go on for the sake of time. So yeah. Okay, I'm gonna try not to get distracted by chat, but here we go. So let's talk about arrays. So here's how arrays are kind of normally how you expect them to. You have a list of things that you can iterate through, but more on that later. So here's how you define an array type. So you just take a type and then you enclose it in square brackets. Yeah, here's an array of numbers. Here's an array of strings. The one thing that's interesting you can do with arrays in Haskell is that you can define a pattern and then you can just do a dot dot and then it'll extrapolate. So here's a list of odd numbers from 1 to 100. So what's happening here is that we have 1 and 3, and then we continue that pattern with 2 dots, and then yeah, that does 1, 3, 5, 7, 9, and so on. You can also do infinite arrays with Haskell. Why does that work? Because Haskell has this weird thing where it's what we call lazy, and that means that it doesn't evaluate an expression until it absolutely needs to. What you can do with that is you can define a pattern and then just do dot dot with nothing afterward. And then what happens is that it basically just keeps that thing as a thing to be evaluated for later. And then when you actually need all the stuff from it, you just calculate everything. So first 20 odds, what we do here is that we can just take the first 20 numbers. Take is a function that takes the first n numbers from an array. And yeah, if you take 20 from odds, it'll start calculating everything, and then you'll get 1, 3, 5, 7, 9, and whatever the first 20 odd numbers are. If you wanted to take a particular number from an array, you can't do the subscript, unfortunately. You can't do the square bracket number. You have to do a double exclamation mark. The reason that it's so clunky is that this isn't really an operator that's used very often in Haskell. But yeah, this is how you would do it. Can you list more than 2 numbers for the pattern? Yeah, you should be able to. I don't know what happens if they're not in the same pattern. I assume the compiler throws an error. We can try that, actually. Oh, wrong one. Let's do 1, 2, 3, dot, dot. I need to do x equals 1, 2, 3, dot, dot, otherwise it will just print everything, and I don't want that to happen. That looks fine, and then x equals 1, 2, 4, dot, dot. Yeah. Any other question for Mla? The double colon declares the type and the equals assigning the array. Yeah, yeah. What happens when you say ask for the 1,000th element from one of the infinite arrays? What happens is that because we haven't actually calculated the 1,000th array, the 1,000th element in the array, it goes ahead and calculates the 1,000th number in the array, and then it takes whatever that number is, and then that's your answer. Can you do patterns other than addition and say 1, 2, 4? I just tried 1, 2, 4 and it doesn't work. So you either have to, the pattern has to either be an arithmetic or geometric sequence. So 1, 2, 3 would work. Actually, is 1, 2, 4 geometric? Would 1, 2, 4 work? It's not. It has to be arithmetic. So that the numbers in between have to be of equal difference. So 1, 2, 3, 2, 4, 6, 1, 3, 5, 5, 10, 15. Yeah. Make sure your indents are right. Oh, I forgot to mention that. Yeah, indents. Very important. It's like Python. If your indents aren't right, the compiler will throw a deceive it. So yeah. All right, I'm moving on then. Let's talk about pattern matching with arrays. So much like other arguments, you can pattern match with arrays. And what that kind of looks, you can do it in a few ways. So just having two square an open bracket close bracket corresponds to an empty array. And there's also this. This means that x is going to be the first element in the array, and x's is going to be the rest of the numbers in the array. So this is actually a library function called map. And what map does is that it takes a function as an argument and an array. And what map will do is that it takes this function, it applies it to every element in the array, one by one. How it does this is that map, we don't care what the function is, it doesn't do anything to an empty array. And if we have an array that's not empty, that can be expressed as x and a bunch of x's, you can do, what we do here is that we apply f to x, and then we append, that's the double colon, that's the double colon up. That's what the colon operator means, is that you take two arrays and append them together. You take this, you calculate f of x, and then you map f to the rest of the elements of x. So recursion, very important. Next example. So here we have a function that basically takes two arrays and adds them together. So as you can see, sum of two arrays, blank r is just the first one. Sum of two arrays, r blank is just the first one. And then if both arrays aren't empty, we take the first element in two, we add them together, and then we append the sum of the rest. Yeah, what Matei said. There are no loops. There are no for loops. There are no while loops. There are no do while loops. Everything in functional programming that requires iteration is done recursively. So there's that to consider. Any questions before I move on? Can we get a single element from array? Yeah, we can. Like I said before, there is the double exclamation operator that you can use to, that basically works like in your Java, you have array, square bracket, index, square bracket. Yeah. So yeah, it does sound okay. What are the middle two lines in that code for? Are you referring to sum of two arrays, or which function are you referring to each time? Yes. So this is just to make sure that we have a case for when one of the arrays is empty. Yeah, it's a base case, as Matei said. Otherwise, otherwise we get an error in runtime, and that would be a problem. All right, I'm going to move on if no one has any other questions. All right, here's some other important library functions that you're going to use with when you're working with arrays in Haskell, and you're going to be using these a lot because these are basically your replacement for this is basically what your replacement for all the loops, because these are all very common sort of operations that you would use when you have an array. So first off, we have filter. So here we define a function that takes an array and only returns an array with even numbers in it. So what we have here is that get evens x's is what you do is you filter. This is a lambda, what we have here. This is an inline function. And we do backslash into the arguments and then arrow to return. So filter x, a function that takes an argument x and then returns whether x is even or not. Well, x mod 2 is equal to 0. And then take that function and apply it to x's so that we only get even numbers. There's also a library function that does this. It's called even. So get even x's is just filter even x's. Yeah. Next up, we have fold. So what fold does is that it takes all the numbers in the, it's a way to take all the elements in the array and consolidate them into one thing. So let's say we wanted to multiply all the elements in an array together. Here we take a function fold. Here we take an array, and then we take the function fold. We use this function that takes an operator, I mean, not an operator, a function, a accumulator, and an array. So in our case, the function is going to be multiply. This is a way to kind of treat the multiplication sign as a function. So it takes two arguments and multiplies them together. Here we have 1, which is going to be our starting value for the accumulator, and x is going to be the nth array, obviously. So what this does is that it takes the first element, multiplies it by 1, the first value of our accumulator, and then we get a thing, and then we multiply by the second thing to get a thing, to update the accumulator again, multiply by the third thing, and so on until we get the value. Fold L1 is a kind of a special case of fold where the initial value for the accumulator is is this function applied to the first two elements, and then you start counting for the third element. So if your array is 1, 2, 3, 4, 5, you take 1 and 2, multiply them together, and then you count from 3. So 1 times 2 is 2, and then 2 times 3, 2 times 3 is 6, 6 times 4 is whatever, and then so on. Yeah. And lastly, we have two different functions that basically allow you to sort of we have two different functions that allow you to take different parts of the array. So we have head and tail. So what head and tail do is that head takes the first item in an array, and tail takes the rest of the items in the array. So yeah, if you ever need to access, it's really helpful in like recursive calls, for instance. So let's say you want to do something with the first part of an array, and then do something else with it, and apply and like recursively call the function on the rest of the array. We do take head nums, do something with it, and then apply the recursive call to tail nums. Yeah. Yeah. That's it for this slide. Any other questions? All right, looks like we're good. Moving on. All right. So I've got another exercise for you guys. So building off of the Pikachu function that we wrote, not Pikachu, the check if a Pokemon started function we wrote earlier, let's apply this to a list. So when we have given a list of Pokemon, let's say we have a list of strings of Pokemon names. Let's determine if the list contains a starter Pokemon or not. Like I said, you should still have this Pokemon starter function from earlier, and if you didn't get a chance to get it working earlier, now's your chance to ask for help in chat, and I'll be there. But yeah, you can use any of the functions that I used in the slides earlier to do this. But yeah, and I'll give you the function headers as well. And we'll take 5 minutes to do that now, so I'm going to pause the recording, and yeah, I'll be in chat. And today's also in chat, so yeah. Hello, you're back. And I'm going to live code it this time just to make sure that it works properly. So what we want to do is we want to check if every single one of we want to check if within our list there is a Pokemon starter. So we can do that. One way to do that is we do it recursively. So let's first write our function definition as starter. Takes a list of strings, oh, no plural, and returns a bool. What we want to do is that first we want to check our base case. So as starter. If our list is empty, it should get false, right? And if our list is not empty, it has x and x's. We want to check if the first Pokemon on the list is a starter Pokemon, and OR it with whether there's Pokemon in the rest of the list. Let's actually check if this works, because that's basically what Ishan wrote. Works for me. Let's do has starter. False, and then let's check this that actually has something in it. That's true. Yeah, is anybody still getting like errors or anything? Because that's what the code is supposed to look like. Could you explain the x-axis part again? Okay, sure. So what the x-axis part is referring to is that x is going to be the first element in the array, and x is going to be the rest of the elements in the array. So let's actually write this out. So if we have an array 1, 2, 3, 5, 6. So what it's going to split this into is it's going to be 1, 2, 3, 4, 5, 6. So it splits off the first element from the rest of the elements. And I'm running my nibble stop. Oh, dear. Might have missed this, but couldn't you just use math? Yes, you could. That is a different solution that I will get into. Let me actually go back to the slide so I can show you. So here's the solution I just coded. Let's see, it's kind of person since we're yeah, exactly. Oh yeah. But let me go through the next solution now. So here's another way you do it. So yeah, this is how you would do it. So first, what's going on here? Let me explain what's going on here. So what's going on here is that we map is Pokemon start to each of the strings in our input array. So that will turn our array of strings into an array of booleans. And the array of booleans will contain whether each corresponding string was a Pokemon starter. So that'll be an array of booleans now. And what we do here now is that we just fold L1 because we use fold L1 here because we're not taking an initial accumulator, and instead what we're doing is that we're just accumulating all of the remember that fold L1 takes the first two elements, takes the function, combines them together, and then does the things with the rest. So yeah, we reduce all of the elements in the array into one single variable that is either true or false. Let me just check if this works so that I can actually show you. So I have starter equals fold L starter string, fold L1, or, and then the map is Pokemon starter string. Okay, that should work. Now, good, that's so good, nice. Okay, I will move on now if no one else has any other questions, unless anyone else still has questions. Feel free to ask now. Okay, I guess we're good, so I'll be moving on then. Okay, so if you've ever coded in Python before, this should look fairly familiar. Haskell also has what are called list comprehensions, which are basically ways to build lists based on different predicates. So, for example, I'm using infinite lists here. Also, we have a list full of multiples of 3, and what we have here is that we take a bunch of elements I from an infinite list. So 1 dot 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 will just do 1, 2, 3, 4, 5, 6 all the way to infinity, and then we want only the i's such that mod I mod 3 is 0. So that'll take all the multiples of 3. And I think I have, yeah, here's the equivalent math way of defining this function. So let me just explain this. So x such that we take a set of x's such that x is 3n for all natural numbers n. So that basically gives you all multiples of 3, all positive multiples of 3, I should say. Here are a bunch of other predicates. So here's not 6. And say you don't like the number 6 for whatever reason. You can make a list that does not contain the number 6. Here's the condition for that. This is how you write not equals in Haskell, by the way. So we take all i's from the infinite list of 1 to infinity, and we take all of them such that they're not equal to 6. Lastly, we have this. So what's happening here is that we can also construct pairs from the elements that we take from different lists. So, but here we have a pair xy where we take x from an infinite list of 1 to infinity and y also from the infinite list of 1 to infinity. What will happen here is that this will create a list of all possible pairs of x and y from 1 to infinity. All right. Any questions about list comprehensions? Sounds good. Moving on. All right. So a lot of you were wondering about. Some of you were wondering about how to take like a different how to take a certain element from a list. What happens if we want What happens if we want to do something with the index? We don't have that information, right? Because we don't have a for loop. I'm going to introduce a function that kind of alleviates this problem. It's called zip. So what zip does is that it takes two arrays and it creates another array that is basically pairwise elements. That takes an element from one array and an element from another array and creates a pair. So as an example, here I have a list of strings, and if I zip it with a pair of integers, what will happen is I get I will get a list of pairs, and it will look like 0, apple, 1, orange, 2, pear, 3, strawberry. And it only takes the size of the smallest list, so you don't have to worry about going on forever. If you wanted to write a function to that, you do this. Yeah, that's basically what that is. Any questions about this, or? All right, looks like we're good. So I have one last exercise in relation to list comprehensions that we can do. Let's try a LeetCode problem. Don't worry, I picked the easiest LeetCode problem. This is two-sum, so we're going to try this now. So here's the problem. Given an array of integers and a target, we return the indices of the two numbers in the array that will sum up to that target. And we assume that any given array will have exactly one solution to this problem. So yeah, so we want to write a function that takes a list of integers and an integer and returns a pair of integers. That will be the corresponding indices to the corresponding indices of the two numbers that add up to that to the target. Anyway, slide. So let's just lay out what exactly we want to do here, which will make it easier for us to actually write the code. So yeah, so we want to generate pairs of indices. And we want to generate pairs of indices so that the answer to the corresponding, so that when we take the elements of the array corresponding to those indices and add them up, we want them to sum them up. We want them to be equal to the target. And just as a reminder, the double exclamation mark is what you use to get elements of the array by index, and that'll be really important in this function. So let me give you a hint. So here's a function signature. This is how you define pairs. So you have an array that you have a function that takes an array. Oh shoot, that's wrong actually. So it should take an int, array of ints, and an int, and return two ints. So let me actually change. Oh, I can't change it right now, but I'll type the function signature out in chat so you guys can actually see that properly. So it should look like that. You have an integer, a list of integers, and an integer, and it should return pair. So anyway, I'll give you parts of this function as well so you guys can actually get started with it. So when we take, oh shoot, I forgot to include the target there. There should be a target there too. But toSum should take an array and a target, and we want to return the first of a list so that you take the first of a list of pairs where you take I from indices and j from indices, and you want I and j to satisfy some predicate that I will leave to you guys to write. And well, I'll leave you guys to it for the next like 10 minutes or so. And if you guys have questions about what to do or any questions about errors about previous code, I'll be here to answer your questions or try to anyway. So yeah, I will pause it right now. All right, we're back. So last part, home stretch. So I've already given you this portion, so you don't have to worry about that. The question is, what elements of I and j do we want to take so that the sum of the elements with corresponding index I and j in the original array will sum up to target. So it's helpful to think about this in a sort of mathy way. We want, first and foremost, we want the corresponding elements of each. So our I plus our j to equal to target. That's a good way. That is basically the condition we want to fulfill. And we also, I don't think we have to put this condition, but I just did it anyway. So for I less than j, I think let's try without let's try without that last condition anyway. Condition first, so we can actually test that out. One thing we haven't done yet is we haven't defined indices. So we want indices to be a list from 0 to whatever the length of the array is minus 1. So we can do that by saying where indices equals to 0 dot length r minus 1. I don't think you need the parentheses, but it's just good to be safe. I think it should work. Okay, let's try it. So we have some array first 1, 2, 4, 5, 6, and let's say we want sum to be 7. Okay, I'll type 1, 2, 6. and 3. So if you notice, the index 0 is 1, and the index 3 is 5. 5 plus 1 is 6. It works. Nice. All right, cool. And I have, okay, that's basically what I have there. And yeah. All right, that's all I had planned for today. If you've made it this far, thanks for sticking it out. I know that this is a really unintuitive topic to learn about at first. So yeah, props to you if you've gotten all the way through. And yeah, hopefully next time I'll be able to clear people up on some of the topics that are. Actually, let me ask chat this right now. Are there any topics that you want me to cover next time that you were confused about this time? That I should just do a quick refresher of before I jump into other stuff. Oh God. No. Lists, pairs, zip thing. Okay, fair. History of Haskell.